Hello, welcome back. Alright, finally the last video for chapter 9 and 25, and this is actually, pardon me for a moment here, this is actually chapter 25. Now we're only doing the first half of chapter 25 because the second half is a complex balancing technique called balancing by the redox half reaction method, and that is an AP chemistry topic, not Chem 1 topic, so we're not going to cover it. All you need to do for redox is understand that redox is a way of classifying a reaction based upon the ability to create electricity. Electrons are going to move from one substance to another, so that movement of electrons creates an electric current. So we could set up a battery and run a battery off of these sort of chemical reactions. Now, do understand that any type of reaction can be a redox reaction other than double displacement, and we'll get into that in just a moment. So what you have to do is, we would give you a redox reaction. You have to be able to assign charges to all the substances, which you've already done. You did that in chapter 7 with nomenclature. And then based upon how the charges change from reactant to product, you have to identify which atoms are oxidizing, which atoms are reducing, and which materials are the agents of that oxidation and reduction. And that's really all you have to do. So we're going to get started here. First of all, redox reaction. Electrons are transferred from one thing to another, and like I said, that movement of electrons creates electricity. If something undergoes reduction, that means you're going to add electrons. So it's going to have more electrons as a product than what the atom had as a reactant. If it's an oxidation, then it's the exact opposite. It's going to lose electrons. It's going to have less electrons as a product than what it had as a reactant. So reduction means your oxidation number becomes more negative when it's a product, and reduction means it becomes more negative as a product, and oxidation means that you're creating a deficiency by losing electrons, so your oxidation number becomes more positive. One of the ways that they teach students to remember this is an old saying, says, Leo says grr. Now, Leo, the lion, is a sign of the zodiac, and lions, of course, growl. So the grr is supposed to represent a growl. And the Leo part stands for, if you lose electrons, then the atom undergoes oxidation. And the GE stands for, if you gain electrons, then the atom undergoes reduction. So I don't remember it that way, but a lot of people do. So you may have seen that before, and if not, you'll probably see it in AP Chem. Leo says grr. So the first thing you have to be able to do to assign reduction and oxidation is to assign oxidation numbers, so you can see how they're changing. So we're going to work out these four. Now the binary ones you've done before, and you might have done a little bit with the polyatomics and the ternaries, but we're going to go over it anyway. Okay, so I'm going to start with the first one, NaCl. You look up the charge of sodium, which is a group 1 metal, so it's a positive 1 charge. You look up chlorine, which is group 17, negative 1 charge. So when they say oxidation number, they mean what is the charge on each individual atom. So I would say the oxidation numbers here are sodium equals positive 1, chlorine equals negative 1. Now with the second example, tin bromide, this is tin 2 bromide. Now you have to use a little bit of algebra. So do understand that total charge is not the oxidation number, so we're going to make a distinction here. If you look up bromine, group 17, its oxidation number is negative 1. However, there's 2 bromines in the molecule, so that bromine creates a total of negative 2 charge. And we can use that negative 2 to figure out that the tin has an oxidation number of positive 2. So again, we would answer oxidation numbers, tin, positive 2, bromine, negative 1. Again, oxidation number, not total charge. Alright, what if you have a ternary compound. We didn't do that in chapter 7. Let's suppose we have 3 elements. The way it works is the thing on the left keeps its normal positive charge, and the thing on the right keeps its normal negative charge, and then we're going to use a little bit of algebra to figure out what's going on with the element in the middle. So we look up oxygen, which has a oxidation state of -2, and we're going to multiply that by 4. That gives us a total charge of -8. But we can go ahead and start answering here, right? Oxidation number for oxygen equals -2. Again, the charge on each atom, not the total charge. But we need the total charge. If we look up potassium, group 1 element, its oxidation number is +1. So let's write that in. Potassium is +1. All right, so far the positives come out to be +1, and the negatives add up to be -8. So what does manganese have to be to balance it? Well, manganese has to be +7 to balance it. So we would say that the manganese oxidation state here is +7. Not hard. A little bit of algebra. Like I said, thing on the right keeps its normal negative oxidation number. Thing on the left keeps its normal positive. The thing in the middle, just use a little bit of mental algebra. The last one, if you have a polyatomic ion, okay. If you have a molecule, then all the charges add up to be 0. However, in a polyatomic ion, this is my total charge. So the total charge is not equal to 0. The total charge is equal to -3. So everything has to add up to be -3 in this ion. So again, we take a look at oxygen, group 16, -2 charge, so we can write oxidation number. Oxygen equals -2. Now there's 4 oxygens, so that's going to add up to a total of -8. So what does phosphorus have to be so that everything comes out to be -3? Phosphorus can only be +5. +5 plus -8 gives me -3. So phosphorus has an oxidation state of +5. So really only 2 adjustments there. If you have a ternary compound, remember the thing on the right keeps its normal negative oxidation number, thing on the left keeps its normal positive, and then we figure out the thing in the middle. If it's a polyatomic group, instead of all the charges adding up to be 0, now they add up to be the charge on the group. Easy. Put a bunch of those on the test, Mr. Burnett, because we're going to get those right. Now, I said earlier that any type of reaction can be a redox reaction except double displacement. Because in double displacement, you're switching the charges, you're not changing the charges. The same charge goes to a different material. There's no movement of the electrons. But we could do a quick combustion reaction to prove that combustion can be redox, right? Let's say we burn methane with oxygen. That's going to produce carbon dioxide and water. Let's balance this. Okay, so now we take a look at what's going on with the oxidation numbers. The hydrogens are +1. They're not changing from reactant to product. But in methane, if hydrogen is +1, there's 4 hydrogens, so that means the oxidation number of carbon has to be -4. Now, if you look at the carbon in carbon dioxide, the oxidation number on oxygen is -2. That's a total of -4. So that means the carbon has to be +4. Carbon goes from -4 to +4. It is increasing in number. We would say that carbon undergoes oxidation. So carbon atoms are oxidized. All right, so that means that something else has to reduce. And the thing that's going to reduce is the oxygen. And it doesn't matter whether we go to the carbon dioxide or the water, we're going to get the same charge for oxygen on the product side, it'd be -2. But as an element, all elements have a charge of 0. So oxygen is going from 0 to -2, and we would say oxygen atoms are reduced. Now, oxidation and reduction has to go together. If one thing is gaining electrons, it's got to come from something else. All right, so a little term here for you. They're going to ask you to identify the atom that's oxidized, or they may ask you to identify the atom that's reduced. From there, they're going to say, hey, what is the oxidizing agent? Okay, another word for agent means reactant. What reactant is causing oxidation? Well, what's getting oxidized? Carbon is getting oxidized. So what's the other material that's causing that oxidation? We would say that oxygen molecules are the oxidizing agent. In the same sense, what's the reducing agent? Okay, glad you asked. Well, oxygen atoms are getting reduced, so the chemical we add to it is causing the reduction. So we would say our reducing agent, again, we're looking at a reactant. When we say agent, another name for reactant is methane. So individual atoms get oxidized or reduced, but it's the reagents that cause the oxidation and reduction. So again, carbon gets reduced, so the thing you added to that carbon compound, oxygen, is causing the oxidation. Oxygen atoms get reduced, so the things you're adding to the oxygen, methane, is what's causing that. So we would say that that's the reducing agent. So again, atoms get oxidized or reduced. The substances, the reagents that cause reduction are called reducing agents, and the substances that cause oxidation are called oxidizing agents. So they may ask you to identify in a reaction, hey, which of these things is the oxidizing agent? So you would have to figure out which atom is oxidized, and then the reagent that you add to it is the one that would be the oxidizing agent. All right, we'll come back to neutralization in just a second. Let's take a look at another example here. All right, so suppose I have this single displacement reaction, and they want you to find out, okay, first of all, what is oxidized, what is reduced, what is the oxidizing agent, and what is the reducing agent. So go ahead and pause and work that out. I'll wait for you. Hey, I'm back. Here's the answer. Copper starts out as an element, so it has 0 charge. And if you come over here, chlorine has a -1 charge, so therefore the copper has to have a +2 charge to balance it. There's your oxidation. We would say copper atoms are oxidized. In zinc, again, the chlorine is -1, so the zinc has to be +2 as a reactant, but it's becoming an element as a product. So it's going from +2 down to 0. We would say that zinc undergoes reduction. So what gets reduced? Zinc atoms. All right, so now we look at the copper as a reactant, and we say, what reactant did we have to add to the copper to make it oxidize? Well, it's the other reactant, zinc chloride. And we have to take a look at the zinc, which is getting reduced. What did we have to add to it to make it reduce? Copper element. And there you go, that's it. Don't make it harder than it has to be. That's all you need for that. All right, one last type of reaction. Something called a neutralization reaction. Now, neutralization reactions are a lot like double displacement, but instead of creating a precipitate, the driving force is the production of a water molecule. So with an acid and a base, the acid provides H+, the base provides OH-, so one of your two products is always water. Again, that's the driving force of the reaction. All right, so suppose we gave you this on a test. Acid plus base produces some sort of salt plus water. Now, salt doesn't mean NaCl. A salt can be any ionic compound that's not an acid or a base. Okay, so suppose we're going to react hydrochloric acid and potassium hydroxide. And they want you to predict the product and balance the equation. Alright, well, it's a lot like double displacement. We're going to separate these into ions. H plus, Cl minus. For potassium hydroxide, K plus, OH minus. And then you just switch the ions. The H plus goes with the OH minus to give you water. And then the salt, K plus goes to Cl minus to give you potassium chloride. And that's it. It is